What if there was a way to divide and conquer data science problems? A way to combine simple models to work together to solve complex tasks? Consider this dataset of students passing or failing an exam based on the length of the exam and the amount the student studied for it. Recall that logistic regression tries to find a threshold that distinguishes points in one class from points in another. But what if these students in the bottom right actually failed the exam? In this case, there is no line that can distinguish students that passed from students that failed. But could we use two logistic regression models to solve this task? I'd like to show you neural networks from a divide and conquer perspective, as a collection of simple models working together to solve a complex task. From this idea, we'll look at all aspects of neural networks, from the ground up, and hopefully demystify how they work and how to set them up for success. This is how I think about neural networks. The goal of logistic regression is to find what sets things apart. For example, we have this dataset of students passing or failing an exam based on the length of the exam and the amount the student studied for it. Our goal throughout this video will be to figure out exactly what sets apart students that passed from those that failed using only study time and exam length. Logistic regression is just one of many tools in machine learning that can be used toward this task. What's nice about logistic regression is that it's relatively simple. The threshold it finds to set things apart is a line representing, in this case, a linear relationship between study time and exam length, which might not always be the best idea, but we'll get to that. The equation of the line that logistic regression found in this case is exam length equals study time. Students on the right side of the line all studied more than their exam's length, and students on the left studied less than their exam's length. We'll rewrite this equation as study time minus exam length equals 0. Although you may be less familiar with the equation of a line in this form, it's a crucial step to unlocking the secrets of logistic regression. We can interpret this line as meaning students need to study at least as much as the exam is long in order to pass. But if a student just barely studied more than their exam length, we can't be that confident they will pass the exam. At least not as confident as we would be for a student who studied significantly more than their exam length. Turns out that the threshold from logistic regression not only distinguishes students as passing or failing, it also assigns a corresponding level of confidence to each student based on how close they are to the boundary. Let's take a closer look at the equation of this threshold. Plugging any student's study time and exam length into that equation, we will either get a positive or negative result. And this will tell us on which side of the threshold the student lies. For example, if a student studied 2 hours for a 1-hour exam, the result will be 2 minus 1 equals 1. All students who studied 1 hour more than their exam is long are on this line. All students whose result is 2 are on this line, and all students whose result is 3 are on this line. The farther from 0 the result, the farther from the line the student lies. These results sort of tell us how confident we can be that a student will pass or fail the exam, but they're difficult to interpret. To translate these results into probabilities, which are more interpretable, logistic regression makes use of the sigmoid function. Although it has this complex-looking mathematical formula, the sigmoid function is just a process that converts numbers into probabilities. It converts large positive numbers into very high probabilities, large negative numbers into very low probabilities, and numbers close to 0 into a probability close to 1/2. Which aligns nicely with the results we obtained earlier by plugging study times and exam lengths into the equation of the threshold. When a point is on the threshold and the result is 0, we are the most uncertain we can be, and the sigmoid function will convert that result into a probability of 1/2. Students far from the threshold will be assigned probabilities of passing the exam closer to 0 or 1. I know what you're thinking. Okay, I get that by plugging study times and exam lengths into the equation of the threshold, we can get a sense of how close or far students are from the boundary. And we can plug these results into the sigmoid function to get probabilities which represent how confident logistic regression is that this student will pass the exam. But how do we find this threshold? Notice that there are infinitely many of the same threshold since we can just multiply it by a constant. Multiply it by 2 or divide it by 2, the line stays the same. Which makes sense. Saying study time needs to match exam length is the same as saying twice your study time needs to match twice your exam length. But if we multiply study time and exam length by different values, let's call these W1 and W2 respectively, We can change the orientation of the line. By adding or subtracting a constant, let's call it b, we can shift the line. These three parameters, w1, w2, and b, completely determine the position of the line. So how do we find the right parameters of the line? Notice that if the threshold is in a position where students that failed the exam are on the right, or students that passed are on the left, it's making mistakes. Since there are three parameters that determine the position of the line, one simple thing we can do is to increase or decrease each of them to see if that reduces the number of mistakes. For example, we could increase W1 by a tiny amount, let's call that amount epsilon, or decrease W1 by that same tiny amount, and we can compare the two. We can do the same to W2, and to B. The best next position is then the combination of the best adjustments to each of the respective parameters. In practice, though, we need to be a bit more careful. Not all parameters affect the line the same. And at this current location, for example, the number of mistakes made seems to be very sensitive to shifting the threshold compared to rotating it. So we cannot change these parameters by the same tiny amount because each of these parameters affects the number of mistakes made differently. To understand how to change the relative size of each of these nudges, we need to dive into some calculus. Notice that instead of counting the mistakes made, we can evaluate mathematically how well the threshold is distinguishing students that passed from those that failed simply by multiplying the probabilities it assigns to points in our dataset. This is called the likelihood function. If the threshold is positioned in such a way that all students that passed are assigned a probability of passing of 1, and all students that failed a probability of failing of 1, then the likelihood is 1 times 1 times 1, etc., which is just 1. Any other probabilities result in a smaller likelihood. The better the threshold is at distinguishing students that passed from those that failed, the closer the likelihood function is to 1. Let's go through a quick example where there are only two students. One studied 8 hours for a 2-hour exam and passed, the other studied 6 hours for a 4-hour exam and failed. Let's say we guess that the threshold is study time minus 2 times exam length plus 3 equals 0. What is the likelihood of the data given the threshold? We first plug the points into the equation of the threshold, then convert these results into probabilities of passing the exam using the sigmoid function. Notice that this logistic regression model is assigning a high probability of passing to a student we know failed the exam. Since the probability of failing is just 1 minus the probability of passing, the probability of failing assigned by this logistic regression model is very low. We can see this reflected in a low likelihood of 27%. Let's see how this compares to a different threshold. Let's try study time minus 2 times exam length equals 0. Notice how this logistic regression model assigns a high probability of passing to the student we know passed and a high probability of failing to the student we know failed. This is reflected in a much higher likelihood of 86%. The goal in logistic regression is to find the values of W1, W2, and B that make the likelihood function as close to 1 as possible. I know what you're thinking. Why use the likelihood function and not simply the number of mistakes made? Great question. What the likelihood function tells us that the number of mistakes doesn't is the severity of the mistakes. Caring about the likelihood means finding a threshold that not only minimizes the number of mistakes, but also their severity. Recall from calculus that finding what makes a function as large as possible involves taking derivatives. Practically, though, we don't use the likelihood function directly because it's not mathematically convenient. We use a different function that is mathematically equivalent but easier and more convenient for our computers to work with. Notice that the values of W1, W2, and B that make the likelihood function the largest are the exact same that make the natural log of the likelihood the largest. Transforming the likelihood function in this way turns the product of probabilities into a sum, which makes working with derivatives easier. Convention in machine learning is to minimize things because this matches our intuition of reducing the number of mistakes. So we take the negative of this function to transform it into a minimization problem. This is called the negative log likelihood because, well, we took the negative of the log of the likelihood. Both the likelihood function and the negative log likelihood express the exact same goal. The negative log likelihood simply phrases it in a way that is easier for our computers to digest. So the new and improved but actually exact same goal of logistic regression is to find the values of W1, W2, and B that make the negative log likelihood as small as possible. The partial derivatives of this negative log likelihood function with respect to each of the parameters tell us how to adapt the relative size of each of the nudges we make to W1, W2, and B depending on the location of the threshold. Gradient descent is a process that repeatedly nudges each of these parameters using this information to eventually find the values of W1, W2, and B that generate a threshold which separates our data well. If you need a more extensive review, I've linked my videos on logistic regression and gradient descent in the description. Now, it's time to dive into neural networks. Chapter 1. The idea. Let's keep going with our dataset of students passing or failing an exam. But with a twist, students in the bottom right actually failed the exam. In this case, there is no line that can distinguish students that passed from those that failed. But maybe we could use two lines. So we're looking for a way to use two logistic regression models to solve this task. Forget for a second how we got these two lines. How do we combine them to determine that it's the region to the right of the purple line but to the left of the blue line where students passed? Well, each of these lines is the threshold from a logistic regression model, and in the context of neural networks, I've found it helpful to think of logistic regression as mapping our data points to the interval 0, 1. Which might be obvious since logistic regression generates probabilities, but bear with me for a second. The blue model maps data points in the 2D plane of study time and exam length to the interval 0, 1 in the following way. While the purple model maps data points to the interval 0, 1 in this way. Just like we plotted our data based on exam length and study time, let's plot our data based on the purple and blue mappings. With the x-coordinate being the purple mapping and the y-coordinate being the blue mapping, we can visualize our data in this new 2D plane. Notice anything? Here, in this 2D plane, there absolutely is a line that can distinguish students that passed from those that failed. The features describing students in our dataset were study time and exam length. These are inadequate in helping us distinguish students that passed from those that failed simply using logistic regression. The blue and purple logistic regression models create a new feature space better suited for the task. In this feature space, students that passed are linearly separated from those that failed, which is ideal for a third logistic regression model to accomplish the task. Notice that the region of the blue and purple feature space where this third model identifies students as passing the exam corresponds exactly with the region of our original feature space between the two dotted lines. If this third logistic regression model were different, that wouldn't be the case though. So combining our two models to determine that it's the region to the right of the purple line but to the left of the blue line where students passed involves a third logistic regression model. Putting it all together, to solve this complex task, we used three logistic regression models. Two to transform our feature space into one better suited for the task, and a third to solve the problem in that new feature space. These three models need to work together. If the first two generate inadequate features, the task of the third model will be impossible. But even if the first two generate good features, the third model still needs to do its job and separate those students that passed from those that failed. A collection of models working together to accomplish a complex task is a neural network. The more complex the task, the more models we need in order to divide and conquer the problem. I know what you're thinking. Okay, the idea of getting models to work together sort of makes sense, but do you have a more concrete example? What are these two logistic regression models learning, if not whether a student passed or failed? One fun interpretation is the following. Let's say the blue model is distinguishing stressed students from not stressed students. Let's also say the model in purple is distinguishing confident students from not confident students. Together, these models split up students into three groups. those that are stressed and confident, those that are not stressed and confident, and those that are not stressed and not confident. Interpreting our data in this way, we see that this group of students in the top left seems to just not care about the exam. They're not confident, but they're not stressed about it. Meanwhile, the stress of students in the bottom right seems to have come in the way of them passing the exam. In this new feature space of confidence and stress, students that passed are linearly separated from students that failed. We call this new feature space our hidden feature space. Hidden because it's not directly available in our dataset. It was discovered by these two logistic regression models. A third logistic regression model in this hidden feature space helps us translate these combinations of stress and confidence into probabilities of passing the exam. Just to confirm it works, let's apply this third model in our original feature space. We first derive the probabilities of confidence and stress from exam length and study time. The following are the approximate values assigned by each model to the various regions of the space. Plugging these probabilities into the equation of the third model, we generate probabilities of passing the exam that align well with the data we have. So from these two intermediary models, we can create a third logistic regression model to solve the overall task. I know what you're thinking. Okay, I get that these two intermediary models are describing students in a way that makes it easier to solve the overall task, but how does that work? How do these models actually communicate and work together? Notice that the performance of the third model depends on the hidden features learned by the first two. The third model evaluates its performance in the same way a logistic regression model would, using the negative log likelihood. Based on its performance, it not only tries to adjust itself to do better like a regular logistic regression model would, it also propagates that information to the first two models so they too can make adjustments to produce better hidden features. This information takes the form of gradients in a process called gradient descent, which we'll look at in detail later in this video. This feedback loop is the learning process of a neural network. This animation shows a neural network learning to bend the original feature space so that students that passed become linearly separated from students that failed, and a logistic regression model can slice through them. Let's take a moment to examine this new structure. This is our input space. It's where our data lives based on how it's described and characterized in our dataset. In this example, our input space is the 2D plane of study time and exam length. Then we have a hidden feature space, extracted by, in this case, two logistic regression models. This is the feature space that is better suited for the task. A task that is more complex may require more hidden features. In this example, exam length and study time get mapped over to the 2D plane of confidence and stress. Finally, we use those hidden features to accomplish the complex task. In this case, we're using a third logistic regression model to do so. Okay, I get that these two intermediary models are learned thanks to the information propagated to them by the third model, but how do we know that these hidden features are actually confidence and stress? Our dataset consists only of student study times, exam lengths, and whether they pass the exam, so where did confidence and stress come from? Great point. The answer is we don't. I use confidence and stress to keep things a bit more concrete and hopefully easy to understand, but in reality, the hidden features are just detecting the presence or absence of some characteristic that helps us solve the overall task. What these characteristics being detected are is unknown. Explaining these hidden features is still very much an active research area in neural networks. Still, I'd like to show you how I think about these characteristics from a purely practical perspective. Picture the hidden features as light bulbs that react to the presence or absence of characteristics in the data being fed through it. A light bulb turns on for a given data point if its probability of having that characteristic is close to 1. If a data point exhibits a certain set of characteristics, the corresponding light bulbs will turn on. While we may not know what these characteristics are, looking at the light bulbs flashing can give us some very practical information about the characteristics being detected. Consider, for example, feeding data points one at a time into the following neural network. Notice anything? The feature at the top seems constant. It flashes on for every data point. This is not a useful feature. A characteristic present in every data point cannot by definition be used to further divide and conquer the problem. If all students were confident or none were stressed, the task would be just as complex in the hidden feature space as in the original feature space. Consider this next example. all features always flash on at the same time. For all intents and purposes, then, these features are all detecting the same characteristic, a redundancy that too inhibits our ability to divide and conquer. The power of a neural network is in its structure, which theoretically allows for simple models to work together to solve complex problems. Practically, we want to make sure that this structure is utilized to its maximum potential, and peering into the inner workings of neural networks in this way intuitively lets us understand that the following structure is underutilized. This network is either unsuccessful in solving its complex task, or the task is very simple, allowing for redundancies. Meanwhile, the following neural network is very well utilized. It's working as best it can given its structure to solve its complex task. If it's still not solving the task despite it working as best it can, we can simply add more models to further divide and conquer. Neural networks then can theoretically solve any problem so long as we can keep combining models to match the complexity of the problem. But practically, there are some major issues. Before we dive any deeper, let's quickly recap. We first learned to think of neural networks from a divide and conquer approach. If one logistic regression model allows us to use one line to distinguish points, then solving a complex task that requires more lines means using more logistic regression models. These logistic regression models transform our feature space into one better suited for the task. But this neural network structure, which theoretically allows for simple models to work together to solve complex problems, is only as powerful as the features it extracts. While we don't know concretely what characteristic each of these features is detecting, by thinking of a neural network as a collection of flashing lights, we can make sure that its structure is utilized to its maximum potential. If it is, but still not solving the task, we can simply add more models to further divide and conquer, at least in theory. In practice, it's very challenging to get these networks to actually learn and accomplish their task. The first of these challenges being how much work the learning process requires of our computers. Chapter 2. Computational limitations. As we scale this structure to solve increasingly complex problems, the iterative feedback loop that allows neural networks to learn becomes increasingly demanding. Every model in our neural network is a logistic regression model and has a set of weights and a bias that defines it, each of which are updated throughout the learning process. The more weights and biases, the more challenging it becomes for our computers. Can we reduce the strain on our computers without compromising the power of neural networks? Consider this dataset of students passing or failing an exam. We could use 4 lines to generate hidden features that will successfully help us solve the task. We sadly can't visualize our data in that space since each point now has 4 hidden features, which means we'd need 4 dimensions to do so. The last model is a logistic regression model of these 4 features, so it has 5 parameters that define it, 4 weights, 1 for each feature, and a bias term. But notice what happens if we use the following 2 lines to transform our feature space. Recognize this dataset? In this hidden feature space, the data looks exactly like our previous example, which we know how to solve using a neural network. From this set of hidden features, then, we can learn yet another set of hidden features, let's call them 2 layers deep hidden features, to help us solve the complex task. This is what such a layered neural network looks like. It maps the original features to a hidden feature space, which is in turn mapped to yet another hidden feature space where students that passed are linearly separated from those that failed. I know what you're thinking. Hold on, that's still 4 hidden features even if they're in a different configuration. What's the difference between this and using 4 lines to solve the original problem? The difference is in the number of weights and biases in this network. The number of weights and biases in our layered neural network is 2 weights and a bias times 2 for the first hidden features, same for the second layer of hidden features, and another 3 for the final logistic regression model. That's a total of 15 parameters. In the shallower neural networks, the number of weights and biases is 2 weights and a bias times 4, and another 5 for the final logistic regression model, for a total of 17 parameters. By layering hidden features, we managed to not only solve the complex task, but we did so by combining models in a more efficient way, reducing the amount of work our computers have to do to accomplish the same task. This is a powerful discovery and a real breakthrough in neural networks. One way to think about layering hidden features is as composing them to more efficiently represent patterns and symmetries in our data. For example, consider that our shallow network has unique combinations of lights being on or off to represent each region of the space, while our deeper network can reuse certain combinations for different regions of the space. But there's a reason beyond efficiency to use deep neural networks. Simply put, we want neural networks to learn instead of memorize. Shallow networks can perform well by increasing the size of the hidden layer, but this puts it at more risk of simply memorizing the entire dataset rather than actually learning the patterns it exhibits. Deep neural networks have the potential to learn higher level features in deeper layers, and this can be encouraged with a funnel-like architecture, decreasing layer sizes through the network. In practice, however, even this new structure is still very demanding on our computers, and for many datasets and use cases past a certain scale, is unusable without a supercomputer. To understand how to make neural networks more cost-effective, we need to dive into the math behind how the learning process works. If you have an aversion to math, feel free to skip ahead to the 30-minute mark. Recall that in logistic regression, we use the negative log likelihood to evaluate the performance of our model, and we use gradient descent to nudge the weights and bias of our model in the hopes of decreasing the negative log likelihood and improving how well our model distinguishes data points in each class. We'll follow the exact same process for neural networks. Consider the following neural network we've been working with so far. We'll keep the notation abstract, but if it's helpful, you can think of x0 and x1 as study time and exam length, and h0 and h1 as confidence and stress. We'll call y the binary variable capturing the class that each data point belongs to. In our example, y characterizes whether a student passed or failed the exam. Because we're trying to model the probability of passing given x0 and x1, yi will be 1 if student I passed and 0 if student I failed. To compute the probability of passing assigned by this neural network to student I, which we'll call pi, we first need to compute the specific levels of confidence and stress of student I given their specific study time and exam length. That is, we first need to compute the intermediary values h0 and h1 that depend on the x0 and x1 characteristics of that student. Each of these vertical sets of values is a layer, and we'll compute things from left to right layer by layer. h0 is the sigmoid of a linear function of x0 and x1 with the following weights and bias. h1 is also the sigmoid of a linear function of x0 and x1 with a different set of weights and bias. The superscript is 1 because these are the weights and biases of the first layer. The first subscript matches the hidden features subscript. So all w1 sub 0s belong to the model that creates h0, and so does b1 sub 0. The second subscript matches the subscript of x. Finally, we get the probability of y by taking the sigmoid of a linear function of h0 and h1. We'll also distinguish h0 as the output of a sigmoid function from hnet0, which is the input to that sigmoid function. We can now evaluate how well our neural network describes the data we have by comparing the probabilities it assigns to our data, which we now know how to compute, to the classes recorded in the data. Exactly like logistic regression, we'll use the negative log likelihood to do so. Notice that every single weight and bias defined in this neural network contributes to the calculation of the probability of y, or the probability of passing the exam. So when our neural network makes a mistake, we need to first unravel how much each component contributed toward this mistake. Do the hidden features need to improve? Or are the hidden features good, but it's the final logistic regression model that needs improving? Partial derivatives with respect to each of the weights and biases tell us their respective contributions. Together, they form the gradient used to update and improve the network. Let's take this one layer at a time, starting with what we know best, a logistic regression model of y given h0 and h1. Note that I won't go through the step-by-step derivation of these partial derivatives in this video. I assume the viewer has taken calculus and can reproduce these derivations on their own. Taking the partial derivatives with respect to w2 and b2, we find familiar equations. This time, though, they're a function of our hidden features instead of our original features. Taking the derivative with respect to w1 and b1 is a little trickier because w1 and b1 are nested in the sigmoid functions of h0 and h1. Let's just focus on a single weight w100 since the computation is similar for the remaining weights. In order to compute this partial derivative, we need to use the chain rule, which gives us the following equation. One we'll come back to frequently because the source of many challenges to come are hiding within it. At this point, we have all the partial derivatives that make up the gradient of the negative log likelihood. and we can take a step in the direction opposite to the gradient in the hopes of decreasing the negative log likelihood. Let me know in the comments if you'd like to see a step-by-step example of using gradient descent to update the parameters of this neural network. When a neural network makes mistakes, we unravel how much each parameter is responsible for these mistakes by computing the gradient, which we then use to make adjustments to hopefully reduce the severity of mistakes made by the neural network. The learning process is a computationally challenging task because calculating each of the partial derivatives that make up the gradient involves a sum over every data point in our dataset, which gets worse as the data and network grow. And this sum needs to be computed at every iteration of gradient descent. We can't control the number of gradient descent steps it will take to get to the best solution, but if we make the gradient computation faster, we can make each step faster and thus the whole learning process faster. But how? Graphics processing units, or GPUs, were invented to speed up the process of rendering graphics as video games and animations became more complex and high resolution. Composed of thousands of workers, each able to calculate things simultaneously in a coordinated way, GPUs can calculate at the same time the millions of colors required in each frame of a video game or animation. Similarly, our gradient computation involves many independent calculations that can be done simultaneously in batches. If we could use some of the GPU's workers to do these calculations at the same time, we could improve the speed at which the entire gradient is computed by orders of magnitude. Still, this computation is only as fast as the slowest worker, and many improvements can be made. But for now, the key takeaway is that thanks to GPUs, we can split up the gradient computation into batches that can be calculated simultaneously, improving by orders of magnitude the speed at which calculations of gradients, such as this one, are made. Looking a little closer at these equations, though, we notice another opportunity for reducing its computational strain. Notice that they all depend on how well the probabilities assigned by our neural network align with the data we have. This is a redundant computation as we would have to calculate it for W1, W2, B1, and B2. To avoid this redundancy, we can first compute the gradient of W2 and save these values so we don't need to compute them again. We then, in a next step, compute the gradient of W1, reusing the values we saved. By moving backwards from the last layer to the first layer and propagating the saved values along the way, we found a way to speed up gradient descent, an optimization called backpropagation. With these two optimizations, our computers can finally start the learning process. But how to kickstart this process so that learning can happen in a reasonable amount of time is extremely tricky. To recap, the strain on our computers is too high to reasonably use neural networks as datasets and tasks grow in complexity. Layering hidden features allows the creation of higher-level features that better represent patterns and symmetries in the data to more efficiently solve the task at hand. Still, the learning process is too demanding, with gradient computations requiring sums over the entire dataset and redundant calculations at every iteration of the learning process. Distributing the computation of the gradient by splitting our dataset into batches allows GPUs to help us compute the gradient in parallel. By computing gradients backward from the last layer to the first layer, saving certain calculations along the way, we can avoid redundant computation to further reduce the strain on our computers. Now that we can finally make use of neural networks on our computers, however, we realize that kickstarting the learning process so that learning can happen in a reasonable amount of time is extremely tricky. Chapter 3. Kickstarting the learning process. Kickstarting the learning process is very delicate and can considerably impede or even completely neutralize the network's ability to improve at its task. To kickstart the learning process, we need an initial guess, which we then nudge repeatedly in the hopes of solving the task. Depending on this initial guess, the learning process could be a success, a failure, take a long time, or a short time. In logistic regression, we can sort of get away with a simple random guess for the initial weights and bias that define our model. But in a neural network where there are considerably more weights and biases, each connected in very intricate ways, we need to give the initial guess some serious thought. Let's go back to the gradient of W1. Notice how it depends on W2, which intuitively makes sense since improving the hidden features should depend on the model that's using them. But this means that how we initialize W2 directly impacts how well W1 will be able to update. For example, if W2 is initialized to a value of 0, the entire gradient of W1 will be 0, and W1 will not be able to update or improve until W2 is updated to a value that is non-zero. The gradient of W1 also depends on the derivative of the sigmoid function, and this is a key difference with logistic regression. When this derivative is small, the entire gradient is very small and the weights W1 update very slowly, which is fine if this coincides exactly with points that are classified correctly, i.e. when pi minus yi is also small. But if the derivative is small when points are misclassified, it's a problem. The weights need updating in order to improve the performance of the neural network, but this can only be done very, very slowly. I know what you're thinking. Why not just increase the step size in gradient descent? Great question. The issue is that a step size that works for the small gradient of W1 might be too big for updates to W2. Okay, then why not define a step size for each layer? That is actually a great idea, and some optimizers like Adagrad have even taken it a step further to define and adapt learning rates per weight and per bias. But this isn't addressing the real problem. Visually, the derivative of the sigmoid function looks like this. It has a bell-shaped curve, and its output is very close to 0 past a certain range of inputs. So when hnet is a very large positive or negative number, the derivative of the sigmoid is close to 0 and the entire gradient is small. This happens if the bias is too large, shifting things too aggressively, if the weights are too large, overinflating the output of the linear function that is hnet, or if the data itself are very large positive or negative values. I like to think of initialization again from a divide and conquer perspective. With each component of our neural network, we're cutting our data into a number of regions in the hopes that they successfully help us separate our classes. The weights are what define the orientation of the cut. We want initial cuts to have the freedom to be in any direction. Even better, they need not be centered at 0. We would like initial cuts anywhere in the range of our data. Shifting this line so it can move freely in this range is done thanks to the bias term. But if the bias term can take on too large a value, notice that we can overshoot or undershoot our entire dataset, which would create a constant feature as every data point is on the same side of the line, underutilizing our network structure. So how do we concretely initialize the weights and biases to random numbers that fall nicely in this range? Recall that every weight is stretching, compressing, or inverting a given feature. For example, we can stretch x1 by multiplying by a weight of 2, or we can compress x1 by multiplying by a weight of 1/2. We can also invert it by multiplying by a negative weight. Applying these transformations to both features, it can also look like we're rotating the data, in addition to stretching, compressing, or reflecting. So the range of the initial bias very much depends on the initial spread or variance of whatever the weights W are doing to our data, which we'll call our transformed data. For example, let's say our weights can take on any number between -1 and 1 equally. That means that this circle is the maximum range of our transformed data and should also be the limit of the range of possible bias terms B. If the initial weights could take on any number between -2 and 2, now the maximum range of our transformed data has changed. And if we don't change the range of possible bias terms to account for this, we won't have a chance to initialize cuts that are very close to the solution, lengthening the learning process. But recall that in logistic regression, inflating the weights also inflates the probabilities we assign to regions of our space. As a feature in a neural network, we want to avoid overinflating the probabilities of its characteristic too soon. Remember, the goal is for the feature to learn to detect the best characteristic to help the entire network solve the problem. If we overinflate things too soon, the feature will overconfidently assign extreme probabilities across the space, acting like a feature that is set in how it divides up the space. What's worse, the derivative of the sigmoid function will be essentially 0 as hnet will be very large, and the feature will be slow to change. So ideally the range of weights is small, but how small seems to also depend on our data. If our data has very large variance, initial cuts made with small weights can seem overinflated by the magnitude of the data points. If our data has a very low variance, the chance of overshooting or undershooting by the bias term is high. If our data is far away from centered around 0, notice that although our cuts can move freely, the likeliness of actually cutting through our data is very small, and the likeliness of producing a constant feature is very large, which gets worse the farther from centered our data is. This also worsens the network's ability to recover through the learning process because of the minuscule size of the sigmoid's derivative. I know what you're thinking. Okay, stop, just tell me what I need to do already. Alright, so in order for a neural network to learn effectively, we need to first center our data around 0. Then, we need to also normalize our data so that all features have a variance of 1. Weights should be initialized to random small positive or negative values. It's important that the weights at initialization be as varied as possible. Cuts that are too close will be pushed in a similar direction through the learning process because they split up the data in nearly identical ways, and thus their gradients will be similar. The initialization of the bias should be a function of how much of the range of the transformed data we'd like to capture. One option could be to use the 3 sigma heuristic and use a uniform -3,3 to cover most, if not all, our transformed data, which after initialization and given the weights has a standard deviation of 1. Putting it all together in a quick recap, the following neural network seems to have a lot of constant and redundant features, which seem to stick around even after a lengthy learning process. Most likely, the data has not been centered. If even after centering there are many constant features, this may be due to the bias term being initialized to too large a value, switching some of these lights to the constant on or constant off position. If learning is very slow, the data's variance might be high. Consider normalizing. If the issue still persists, it might be the weights are initialized to too large a value. If after training we end up with many redundant features, it may be that the weights and biases are initialized to too similar a value and more randomness needs to be introduced. And this works great for shallow networks. But as we increase the depth of our network, even if we do everything right, we'll end up with a neural network that looks something like this, where features deeper in the network become redundant or constant. It just never ends. Recall that hidden features don't play well with data that isn't centered around 0. But even if we center our data, hidden features are all created from logistic regression models, which means hidden features all lie in the range of 0 to 1 due to the sigmoid function. And these features, all with values between 0 and 1, are the inputs to the next layer, which isn't an issue for a shallow network because these features, if we've initialized things properly, should be distinct and varied. And since the last layer is just a regular logistic regression model based on these features, everything ends up being as fine as logistic regression ever was with non-centered data. But when hidden features are layered together, the hidden features deeper in the network start to become increasingly redundant or constant, which makes the task impossible for our last layer. Why does this happen? We might suspect that the cause is how the data is shifted by the sigmoid function. But the data is shifted the same in each layer, so if that were the case, all layers would be affected equally, not just features deeper in the network. Notice that not only does our data shift to be centered around a mean of 0.5 instead of 0, the spread around the mean, also called the variance, becomes squashed by repeated applications of the sigmoid function. That means that by the last layer, data is highly concentrated around the mean of 0.5 and is thus particularly sensitive to overshooting or undershooting by the bias term, or deflation by the weights. These constant features then become inputs to the following layer, which becomes even more sensitive to this phenomenon. This is called variance squashing, which the learning process cannot get out of because these constant features have a very small or even 0 gradient. But we know this is going to happen in a very predictable way. Knowledge we can use to initialize weights with increasing size throughout the network to counterbalance this squashing and keep the variance constant. One such initialization method is called Xavier initialization. Another solution is called batch normalization, which normalizes HNet before it goes into the sigmoid function of each layer so that all layers behave exactly like the first layer. I know what you're thinking. Surely with all these solutions, our neural network can now utilize the full potential of its structure, right? Right? Well, there's still one tiny issue. And this one could really go unnoticed because there really isn't a way to diagnose it just by looking at the collection of flashing lights. To notice it, you need to keep track of the weights and biases throughout the learning process. If you do so, you'll discover that in a deep neural network such as this one, the weights and biases of the first few layers are barely if at all changed. Meanwhile, the weights and biases of deeper layers are updated normally. The culprit, once again, seems to be the derivative of the sigmoid function. As we increase the depth of the neural network, W1 becomes nested within more sigmoid functions of sigmoid functions of sigmoid functions, and we need more chain rules to extract its gradient. The gradient of W1 depends not only then on the derivative of the sigmoid function, but on a product of these derivatives. Recall that we already had issues with the derivative of the sigmoid being near zero for values beyond a certain range. And as we increase the number of layers requiring more chain rules and more sigmoid derivatives, the effect is compounded, because multiplying lots of small values together makes even smaller values. This means the effective range of values that makes the gradient non-zero is much smaller for earlier layers than in deeper layers of the network. This is called the vanishing gradient problem, because the gradients seem to vanish in earlier layers of the network. I know what you're thinking. Can't we create larger step sizes in earlier layers to counterbalance this? Yes, we can, but it too comes with a set of caveats. More importantly, just like our solution to the squashing variance problem, it doesn't exactly address the root of the issue, the sigmoid function. We need to consider that maybe the sigmoid function just isn't right for creating hidden features. We can still use it in our last layer to classify points given the hidden features, which then allows us to use the negative log likelihood and intuition from logistic regression. But for hidden features, we need to start thinking beyond logistic regression to find a function that solves both the variance squashing and vanishing gradient problems. The first thing we might try is to remove the sigmoid function entirely. It's kind of strange to have features that are only in the range of 0 to 1 anyway. This way, all our hidden features are just linear functions, which solves our squashing variance and vanishing gradient problems. But a linear function of a linear function is still just a linear function, which means that each hidden feature space is just a linear transformation of the previous hidden feature space, which is just a linear transformation of our original feature space. So no matter how complex we make our structure, without the sigmoid function, the entire network collapses to simple logistic regression. We need the sigmoid function to transform our original feature space in a non-linear way, bending and twisting our dataset into a configuration where points in one class are linearly separated from points in the other. So the power of a neural network that allows us to divide and conquer data science tasks might not entirely be in its structure as we previously thought, but in the types of hidden features it's able to create, which so far seems to depend on the sigmoid function. Can we find a different function that addresses both the variance squashing and vanishing gradient problems while preserving the power of neural networks? One option is to find something that imitates the sigmoid function, like the hyperbolic tangent, whose output is centered around 0, thus solving at least the data shift issue, keeping our data centered around 0 at each layer, but solves neither the variance squashing nor the vanishing gradient problems. It just delays them a bit because of the wider range of outputs of tanh, squashing things less aggressively, and the wider range and larger magnitude of non-zero values for its derivative, allowing for a slightly deeper network before gradients start to vanish. But the biggest issue with tanh is more subtle. With sigmoid, features are basically deactivated when data points don't exhibit a certain set of characteristics. The weights attached to these features in the next layer are then inconsequential in how the network makes predictions, because the output of that feature is 0. So if a data point doesn't have a given characteristic and the feature is deactivated, the output is 0, which neutralizes its contribution to the following set of hidden features. This makes the learning process simpler since you'll remember we adjust weights based on their contribution to mistakes made by the network. And in this case, they don't contribute, so they're not updated. With tanh, the output is never 0, meaning all features always contribute. This makes learning less efficient and at the same time makes understanding what contributes to a data point's classification challenging. I know what you're thinking. Hold on. The sigmoid function is never actually 0 either, so isn't it technically just as inefficient as tanh? You're absolutely right. The simplification was to demonstrate how much an ability to deactivate a feature by having its output be 0 is valuable. Notice that there does not exist a linear function that can be 0 on a set range of values. So the act of deactivating features introduces nonlinearity in how we transform each hidden feature space. And nonlinearity is exactly what allows us to go beyond simple logistic regression. Let's go back to our linear function, which solves both the variance squashing and vanishing gradient problems. and rectify it so that in a specific range of values, its output is deactivated. This piecewise linear function is called the rectified linear unit, or ReLU for short. And I know, this function isn't differentiable everywhere. But gradient descent still works because it's piecewise differentiable, which is good enough. What's more, the gradients become very simple, which speeds up the learning process considerably. Using the ReLU function instead of the sigmoid to generate hidden features is an incredible breakthrough in the development of neural networks. But no function is perfect, and features that have become constantly turned off can never recover as the gradient is exactly zero. With sigmoid and 10H, these were essentially zero, but it was at least possible for them to recover in the long run. With ReLU, this is completely impossible. This motivated the creation of the leaky ReLU function, which isn't exactly zero when the input is negative, just very, very small. Now, there are a ton of functions to choose from, each with their unique set of strengths and caveats. To recap, despite following the best practices for initializing the learning process, deep neural networks, as we've constructed them, suffer from issues that impede its ability to learn. The sigmoid function repeatedly squashes hidden features, making it more likely to overshoot, undershoot, or deflate deeper features in the network. The weights and biases of earlier layers are also rarely updated. Gradients intended to update these earlier layers seem to vanish because of repeated applications of the chain rule involving a function whose output is very small. The culprit is the sigmoid function. It's inadequate in creating hidden features, especially in deep neural networks. Changing it out for the hyperbolic tangent, which still suffers from the same issues, we notice that a valuable tool is an ability to deactivate features completely, which we use to create the rectified linear unit, or ReLU, and a slew of other functions. We've come a long way in this video from logistic regression to deep neural networks. We learned that neural networks are a collection of simple models working together to transform our data layer by layer into representations better suited for the complex task. Along the way, we optimized their learning process, improved their efficiency, and even replaced components to overcome their challenges. But for all their potential, neural networks are far from perfect. They struggle with finding repeating patterns in our data. They struggle to recognize the same pattern in different regions. They cannot adapt to different contexts. Each of these limitations reveals something deeper. Neural networks don't understand the way we do. They're a rigid mathematical process, and at the end of the day are just solving a mathematical problem that isn't necessarily representative of reality. So while we've answered many questions in this video, the truth is, we're just getting started. Like, subscribe, and help me spread this knowledge around if you found it helpful.